In this video, we're going to see again briefly what series resistors are, what parallel resistors look like, and then we'll learn some equations for parallel resistors, and finally we'll see an equation for power dissipated by a circuit. Now let's say we have a series resistor, a series circuit like this. Why is this circuit a series circuit? Here's the reason. Charge which leaves from the battery, right? Here's the battery, and it leaves from the big terminal. It goes out into the circuit, it passes through the first resistor, then through the second, and then it comes back up to the top. The battery uses some of its juice to pump it up to energize it again, and then once it has energy, it goes through again, it bounces through, whoops, the charge bounces through, it loses some energy in here, then it bounces through and it loses some energy in there, and then it comes back to here, it's energized, and it repeats, right? There is one pathway through the two resistors X and Y, and because there's only one pathway through X and Y, we say that those two resistors are in series. The other way it can look is like this. It can be a parallel arrangement. So we have a battery, and we have one complete pathway through that resistor, but then we have a second complete pathway, whoops, through another resistor. So for example, let's call these resistor X and Y. Let's say we have a charge, a couple charges maybe. Here we go. The charges come down, they get to here, and uh-oh, they have to choose. Maybe one goes that way, and then comes back to the terminal, but the other goes this way, and then back to the terminal. So what it would actually look like is more like this. They go down, they split, one goes here, the other goes here, and then they sort of join back up here and return to the terminal together. The charges never loop around on themselves like this. They never like go back through resistors multiple times or go around like 10 times and then come back over. They always go straight back. They go straight to that terminal as soon as they can. They want the path of least resistance. So if the charge has just passed through a resistor, it's going to take the path of least resistance, which returns it. The path of least resistance is to go along the wire, not to continue going through resistors, because that's high resistance compared to a wire. Okay, so they never loop on themselves, they never loop back again. And what's the distinguishing feature? In this arrangement, there are two pathways through X and Y, those resistors. Therefore, X and Y are in parallel. That's what we mean when we say that they're in parallel. So here is how we calculate the equivalent resistance whenever two resistors are in parallel. We want to know what's the combined impact from those two resistors. For a minute, let's call this R sub X, R sub Y. Okay. The way you calculate the equivalent resistance is you take 1 over Req equals 1 over Rx plus 1 over Ry. Now this is a little different, so I want to show you an example. Okay? Let's imagine we have a resistor arrangement that looks like this. We have 8 ohms right here, and then we have 4 ohms down here. We want to know what's the equivalent resistance due to the two resistors together. You use the equation 1 over the first resistance, which is 8, plus 1 over the second, which is 4. We could rewrite this as 2 over 4 I'm sorry, 2 over 8. And what we'll have is 3/8, or Req equals 8/3 ohms. And we can calculate if we want to put it in decimal form. Whoops, decimal form, that'll be 2.67. Right? 2.67 ohms. In other words, if you were to take that circuit and draw a comparable circuit that had just one resistor, not 2 in parallel, just one, then what you would have is one resistor like that with, a smaller resistance. So why is the resistance smaller when you add resistors like this in series? Why does that have a net reduction on the total resistance of the circuit? Why is that? It's a good question. I'm going to let you ponder this. One thing you might think about, one thing you might consider, is the fact that resistivity is inversely proportional to area. By providing a second pathway here, by providing 2 pathways, we are basically increasing the area through which charge can flow, and that lowers the resistance. So consider this, ponder this, think about it, see if it can make sense, if you can find a way to explain it in your own words. Now there's a trick. Many of the problems with parallel resistors will look like this. Many of those problems will look like this. We'll have 10 ohms, and the second parallel resistor will be identical, 10 ohms. You can work out the math, but whenever you have that situation, the equivalent resistance is half. It's 5 ohms. Okay? No matter what the value is here and here, as long as they're the same, you have that value to get the equivalent resistance. There's one final thing for us to learn, and it's power, electrical power. Sometimes a question will ask us, what is the power dissipated by the circuit? Let's take a simple example. Our EMF is 10 volts, and the resistance, the single resistor, has a resistance of 5 ohms. It's like 5 horseshoes. There we are, 5 ohms. The way we find power, the power dissipated, is by multiplying the current in the circuit times V, the voltage dissipated by the circuit. And that's how we find how much power is dissipated by the entire circuit. So, we're going to need to know I. The total current is equal to the total voltage dissipated over the total resistance. And the voltage dissipated is equal to the voltage supplied. If 10 volts is supplied, then we're going to dissipate 10 volts. And the total resistance is just that single 5 ohm resistor. And 10 over 5 is 2 amps. So the power is going to be 2 amps times the amount of voltage dissipated, which is equal to the 10 which are supplied. If you supply 10 volts, then the whole circuit is going to dissipate 10 volts right there in that resistor. So then this will be 10, and we'll get 20 watts. 20 watts. So these problems can be simple, like the one I showed you, or they can be a little more complicated. We could have something like this. Oh, this is fun. Let's say we have an EMF equal to 20 volts, right? 20 volts. And this one here, this resistor is 5 ohms. This is 10, and that's 10. We want to find the power dissipated in the circuit. every time I say circuit, I want to actually say circus. And I don't know how I refrained myself. I want to say circus so bad. Okay, circuit. So, to find the power, we are going to need to know the total current, the total current and the total voltage. Except, we know that the total current in the circuit, V is IR, so current is V over R, like that. And the way we find power will be just as good as we can also find it using this equation. And if we're doing the power dissipated by the whole circuit, then we need the whole voltage on top and the whole resistance on bottom. We already know what the total voltage is. The total voltage supplied is 20 volts. Therefore, the total voltage consumed is 20. But what about the total resistance? That's a little trickier. These two together are in parallel. If a charge were to come out and follow a pathway, it would go through that one, and then it would either go through there, or it would go, it would either go through the top, or it would go through the bottom. So the two 10-ohm resistors are in parallel with each other, and that means that we can erase those two. Right? In other words, these are in parallel, and that parallel circuit is in series with the 5-ohm resistor. So we have both parallel and series at the same time. We can replace the two 10-ohm resistors with a single resistor equal to the equivalent resistance. And of course, the equivalent resistance, when they're in parallel like that, is just half the value. We can use the half trick, the 1/2 trick, because both of the resistors in parallel were 10 ohms. And then we add up 5 and 5 to get the total resistance, and that gives 5 plus 5 is 10. So what would we put in the denominator right here? We would put 10. And when we calculate the total power dissipated by this circuit, we'll have 400 over 10, or simply 40 watts.